Hello, and thank you for tuning in to this paper presentation. My name is Logan Swain, and I'll be kicking off the presentation of my team's most recent publication titled Translating SysML Activity Diagrams for nuXmv Verification of an Autonomous Pancreas. This publication was written by Orion Staskell, Josh Simak, myself, and Christian Rosier. In the landscape of the world today, we are constantly surrounded by software systems. Whether it be the phone in our hands, the smartwatch on our wrist, or even the insulin pump in our pocket, these systems play a critical role in our day-to-day lives. And as these systems become larger and more complex, so too do the methodologies need to accurately design them. One system modeling solution is Model-Based Systems Engineering, or MBSE for short. MBSE is a system modeling methodology that enables definition of large, complex, multidisciplinary systems with various levels of abstraction. It supports requirements, design, and analysis of an entire system within one contained model. While there are a handful of MBSE languages, we will focus on the system modeling language, or SysML for short. SysML is an MBSE specific language that visualizes model information through the use of 9 individual diagram types, each of which achieve specific and independent goals. Further details on the state machine diagram and activity diagrams, which are 2 of the 9 total diagram types, will be given later in the presentation. With the power of SysML, systems can now be defined. But what if the system is safety critical and also needs to be validated or verified? This is where the use of formal methods, and specifically model checking, provides a systematic way of validating or verifying a system. While there are many model checking tools available, our team chose the Symbolic model checker nuXmv, mainly because of the ability to define complex system behavior using its own input language, while also offering strong verification based on cutting-edge SAT-based algorithms that it provides. The model is checked using linear temporal logic, LTL for short, or computational tree logic, CTL for short, specification checking. Each of the specs are checked against the model using nuXmv. nuXmv then outputs either if that LTL or CTL spec is true, if it's satisfied, or false with a counterexample trace, which describes the sequence of events that resulted in that particular formula being broken. The case study that will be presented in the rest of this presentation focuses on the Autonomous Artificial Pancreas System, or APS for short. The APS is a hybrid closed-loop insulin pump system that's designed for patients with type 1 diabetes to help control their blood glucose level while minimizing the need for user input. And it's similar to the commercially available Tandem t:slim X2 and the Medtronic MiniMed 770G. Both of those are pictured at right. The APS is comprised of the artificial pancreas, which itself houses the control algorithm, the insulin supply, and the glucagon supply. In addition, the APS module has a blood glucose meter and offers connectivity to a fitness app, a medical database, and medical care providers. When operational, the system functions in a cycle where the blood glucose meter first senses the patient's blood glucose level. It then performs modulation to determine if the patient needs insulin or glucagon. The system then administers the medication before repeating the process while operational. In the following presentation, we will present a 4-step SysML to nuXmv translation technique, which will be applied to our safety-critical medical device known as the APS through a case study. The case study will demonstrate conversion of the SysML state machine diagram to nuXmv for high-level system functionality. We will also do conversion of activity diagrams to nuXmv for lower-level system functionality. We will derive LTL and CTL formulas from the SysML model for validation and verification. And finally, we will perform model checking using nuXmv. Finally, we will discuss lessons learned and potential future work at the conclusion of this presentation.
In our paper, we propose a 4-step translation process from SysML to nuXmv. These steps are the main module definition, which defines the initial setup and overall structure of the model from the SysML state machine diagram, the submodule definition, which defines the specific submodules we're going to be using and kind of some of the lower level organization, the activity diagram organization, which allocates the activity diagrams into specific submodules, and finally the activity diagram translation, which is actually taking those activity diagrams and translating them into nuXmv code, which is the lowest level setup of the model behaviors. The first step in our process is the main module definition. And this is generally taken from the overall state machine diagram of your SysML model. So for the apps, we created this automaton showing the general transitions and states of the state machine diagram. So we have 4 main states: startup, operational, shutdown, and maintenance, and the arrows between them are showing the general transitions without kind of showing too much of the logic behind them. There is more to this diagram. It is important to note that in SysML, each state is self-recurring. So just because it's in operational mode doesn't mean it needs to transition to maintenance mode in the next step or shutdown. It can stay in operational mode for any length of time. For the apps, it made sense to include the startup and shutdown behaviors in this main module, while operational and maintenance mode both got their own submodules because they have a bit more complexity. Here are the 2 automata we created for the operational and maintenance modes for the second step in our process, the submodule definition. So these 2 were each given their own submodule within maintenance mode, but they contain additional submodules within them. The maintenance mode has a ready for maintenance state, as well as 4 different maintenance tasks, and operational mode has a functional variable, which kind of displays the functionality of the system or if there are any warnings during the operational aspect of the system, and it has 5 different connectable devices. So these maintenance tasks and connectable devices were each organized into their own submodules, and you will kind of see that in a coming slide. But the use of these submodules means that each component of the system can be individually tested against written specifications, and we can make adjustments to those submodules without altering the overall system too much. And it kind of keeps everything easily workable and contained. With these additional submodules, this is the overall structure for our nuXmv model. We have the main module, and then under that we have our 2 operational and maintenance mode modules, which each have their own submodules within them for the maintenance tasks and for the connectable devices. From here, we can do our the third step in our process, which is organizing all of our activity diagrams. So each activity diagram will have one main location or one main submodule where it is placed, but some of the functionality might be captured in multiple different submodules. This is just kind of a general outline and doesn't need to be strictly followed. Once the activity diagrams are organized into their respective submodules, they can be translated into nuXmv code. So this is an example of the shared data with medical care provider activity diagram, or MCP, which has been modeled as a single variable within the MCP submodule within operational mode. This is one of our connected devices. This is one of our more simple activity diagrams, but it still illustrates the process well. As I said, it's a single variable within the MCP module. So this is the patient data variable in nuXmv, and it is only active when the operational mode determines the MCP is in fact connected. So if the system is not in operational mode, or if the MCP is not connected, the status of this variable will always be none. And if at any point it gets disconnected or the system leaves operational mode, it'll immediately return to none. So it starts out by potentially initiating a request for patient data. If the MCP is connected, it doesn't have to initiate a request. It can sit in the none state and kind of be idle forever, or it can initiate a request, in which case the patient data variable changes to requested. After a data request, the variable transitions into the authenticating step. After exactly one time step in nuXmv. In this assignment, the variable can either stay authenticating, which is kind of denoted by that cyan box. It can stay in that state forever, or it can then move to a rejected or provided status. If the request for data is rejected, or if the data is provided, the variable will then return to the none state in the next time step. So that was the entirety of the model for this specific activity diagram, and then this process would need to happen as many times as you have useful activity diagrams. So for example, we had 44, some of which were more complex than this and involved changes in multiple submodules with multiple different variables, but other ones were just like this, where it's a single variable and you need to take the time to go through each step, but it is a relatively simple and straightforward process. Once you have all of these different activity diagrams modeled, you will need to run a set of specifications against your model to validate and verify your system.
In tandem with the SysML to nuXmv conversion, validation and verification specifications were written based on apps functionality. The verification specifications verify that the apps requirement hold for the nuXmv translation of the model, where the validation specifications validate that the nuXmv model performs all the intended functions. One way we ensured verification spec coverage was through using verification benchmarks, which you can see on the right-hand side of the figure. These benchmarks are listed from most important to least important, with safety critical being the most important. In this context, safety critical specifications determined if medication is properly administered while operational. Failure safety checked for proper responses to system failures. Mode transitions focused on pre-transition and post-transition conditions being met. And lastly, connected devices verified that alert messages are being sent and received when a given device is connected. In total, 134 specifications were written, distributed between validation and verification, all of which were debugged using code inspection and satisfiability checking with the universal model. Since these specifications were written while the nuXmv model was being created, some nuXmv model bugs were discovered.
Getting results back from running the specifications against the model gave us insights into the model. The results led to us finding some minor system state bugs and helped us improve the nuXmv model. One bug can be seen here. The system is in operational mode and in a functional state, which is shown by the green box. If a degraded or failed state occurs while in operational mode, the system will transition to maintenance mode. At this point, maintenance tasks must be completed before returning back to operational mode. However, the task priority information is not stated explicitly in SysML, so the nuXmv model was allowed to switch back to operational mode, even when it was in a failed state. By fixing this trace, we were able to learn more about the SysML to nuXmv process. Specifically, SysML does not have task prioritization or system timing information, so not including this information in nuXmv can result in bad system behavior.
Our validation specifications once again check that our nuXmv model performs all of the intended SysML model functions. The specifications themselves were broken up between various categories. Specifically, shutdown mode, maintenance mode, and operational mode, which are the three modes of the app system. We also checked app connectivity and valid variable assignment. In total, 105 validation specifications were written and checked against the completed nuXmv model. All 105 specifications passed as expected. One validation specification example can be seen on the slide in front of you. It states, always not IBIT running and, parentheses, refill insulin running or refill glucagon running or replace CGM running. In more English terms, it states, if the initiated built-in test or IBIT is running, then no other maintenance mode can also be running. This is consistent with how the SysML model is defined and is a critical component of how maintenance mode operates. We would expect nuXmv to output true, and we observed a true outcome, thus validating this portion of the model. For our verification specification results, once again, our verification specifications verify that the app's requirements hold for the nuXmv translation of the model. In total, we created 29 verification specifications, each broken down between the 4 specification benchmarks that you can see on your screen. All 29 verification specifications were run against the nuXmv model and the universal model. The universal model checks to make sure that the formula is not only satisfiable, but also not a tautology. All specifications came back with a passing result as expected. 3 verification specification examples are given on the screen in front of you. All 3 of these specifications are pulled from the safety critical benchmark for verification. In English terms, the first LTL specification states that glucagon will always be delivered when the patient has low blood sugar. The opposite of this is stated in the second LTL formula, that insulin will always be delivered when the patient has high blood sugar. And finally, nothing will be delivered when the patient has normal blood sugar. We would expect that each of these LTL formulas come back true. And when run against the completed nuXmv model, the result is true.
One consideration when translating from SysML to nuXmv is that SysML is at a higher level of abstraction than nuXmv. This means that you may have to make assumptions in order to provide the level of detail needed for a nuXmv model. Examples of this would be the lack of task prioritization and system timing information in SysML and how nuXmv may require that information to avoid unwanted behavior. Very closely related to that is the scope of SysML versus nuXmv. It is important to be sure that the information in the SysML model can be model checked and that the results of the model checking are meaningful to the system. For example, in our case study, the state machine diagram and the activity diagrams provided enough states in mode interaction that we were able to model check the higher level functionality and the interactions between modes. The results are meaningful and they verified the high level functionality of the system. Lastly, when looking to verify a complete system, it's important to model check beyond the SysML model. The software and hardware should be model checked where appropriate, and as well as testing to be performed to ensure that the system meets all of its requirements. As for building off of this case study, it will be useful to have an entire SysML model translated to see how the SysML diagrams interact with each other in nuXmv. It would also be useful to go through the entire system development process, including software and hardware, using a model-based systems engineering approach and model checking throughout the entire process. The value of completing this process would be to analyze what model checking is most beneficial at what stage of development, specifically when using a model-based systems engineering approach and a SysML model for that development. In summary, in our case study, we used a 4-step process to translate SysML functionality to nuXmv using activity diagrams. The first step was to define the main module using the state machine diagrams. We also defined submodules using the state machine diagram in the second step. In the third step, we organized the activity diagrams into their respective submodules and then translated them in the fourth step. By completing this case study, we found that nuXmv may require some information that is not included in SysML, such as task prioritization and system timing information. The results of using this method to model check a SysML model provide insights into the SysML model, as well as verify the high-level functionality of the system.